What?
Hi guys, we're Humic Acid. My name is Carolyn.
I'm Lawrence.
I'm Maya.
Okay, yeah, we're gonna start.
Okay, so first we're gonna tell you a little bit about what humic acid is. So humic acid belongs to a group called dissolved organic matter, which constitutes a large part of natural organic matter. Basically, humic acid is the result of plant and animal decay, and it collects in soils, and soil runoff falls into the water, and that's how it ends in the rivers and streams. Humic acid is essential for plant growth. However, they are not beneficial for drinking water treatment processes. That is because they have negative effects on water quality by causing color and odor problems, as well as increased humic acid causes increased coagulant and disinfectant doses needed to treat it, and that results in increased sludge volumes, which is really hard to take care of, and biological growth within like the plant itself, which also causes more complications. And if humic acid goes untreated in the water, it reacts negatively with chlorine, which causes harmful carcinogenics to be consumed by people.
So in the past, we tried to develop a model where we can see like what the optimal dosage for coagulant would be for different concentrations of humic acid. So as you can see, for concentrations of 5, it would be 1.6 to 1.8, and for 10, it would be at 1.3. So there isn't that big of a difference for different concentrations of humic acid. Therefore, for this semester, we're trying to test to what extent can we remove the humic acid from water, and to what extent can the absorbance change if we use larger concentrations of coagulant. And in addition to that, we're not using clay, so we're also trying to see if flocks can form if not using clay.
So the main difference between this semester and last semester's experimental design is, as Carolyn mentioned, that we're not using clay in our experiment. So instead of 4 pumps, we have 3. Looking at our experimental design, you can see that the water flows into the system, and as the coagulant and humic acid pumps are working, the water mixes in with the humic acid and enters our influent turbidity meter, and then humic acid, water, and coagulant enter the flocculator, which then goes into the recirculator, settles into the sedimentation tank, and then the clean water rises to the top and goes through our spectrophotometer, which measures absorbance, and our effluent turbidity meter. And the schematic is just to clarify where all the connections are. So if our experimental set, like the picture of our experimental setup doesn't make sense, you can just look at this one. So the first experiment we did was using 15 milligrams per liter of humic acid, and then we just varied the concentration between 1.6 milligrams per liter to 2.8 with an interval of 2. So the main thing that we observed was that the absorbance goes down when we raise the concentration of coagulant, and this can be seen when we look at the difference between 1.6 and 2.0 on the table, which is on the next slide. Wherein the change in the absorbance is a lot bigger than the change in the absorbance between 2.4 and 2.6. This indicates that there is a limit to how much the coagulant concentration can be increased before it stops having an effect on removing the humic acid from the water.
So for experiment 2, we changed the humic acid concentration to 20 milligrams per liter, and we varied the coagulant dosages at 2, 2.2, 2.4, and 2.8 milligrams per liter. So as you can see from the data, initially at 2.0, there's a relatively high absorbance, indicating a high concentration of humic acid still in the solution. However, as we increase the coagulant dosages, you can see that the absorbance of humic acid decreases, and it plateaus right around 2.8. So we determined that right around 2.8 would be the optimal dosage here for 20 milligrams per liter solution of humic acid. And this is a table with the same results. Our data was collected at a steady state value that we determined once we saw flocks form in the recirculator. So for experiment 3, we found similar results. This was at 25 milligrams per liter of humic acid. We varied the coagulant dosages at 2.4, 3, and 3.8 milligrams per liter. And as we increase the coagulant dosage, we notice a decrease in the absorbance. So that means a decrease in the humic acid concentration. And it seems to plateau right around 3.8 for 205 milligrams per liter of humic acid. Same thing is represented as this table that you can see here.
So basically, this experiment compared with the previous semester's experiment is that the flocks form at a slower speed, which is expected because we're not using clay. A second difference is that with smaller concentrations of coagulant, there tends to be a smaller difference in absorbance, which is also expected because the pump speed that we're using to get to the coagulant concentration varies very little with the smaller range of coagulant. So this is to be expected. Also, this for our complications part, because each experiment is not done separately, which means that for the same concentration of humic acid, we're not flushing things out and rerunning them. We're actually keeping the humic acid inside, and we're just changing the pump speed of the pumps to get to the coagulant dosage. That might have resulted in some complications, like not reaching the data as we wanted to. So we should be doing more experiments to see what is optimal. And second of all, we have not defined our steady state. In the past, we just defined the steady state as when the flocks form. But in this experiment, either the flocks have formed really slowly, like 3 hours, or after they form, they become bigger at a really quick speed. So we really don't know how to interpret this. And third of all, because the pump speed, the newer pumps have a really slow pump speed, so in this part where the wastewater is supposed to go out, it doesn't. If we open up the wastewater valve, the cleaner water would not go up to here, so we would not actually get a reading. Therefore, we closed the wastewater valve, and so none of the flocks could go out. We would occasionally open it up so that some of the flocks could go out, but we're not sure how that would affect the experiment. Again, we're not sure if this is changeable because of the pump speed. So yeah, these are the complications.
So here's the Python code that we use to determine the pump speed that we should set the pump to in order to achieve a specific concentration of humic acid and fluorocoagulant in the recirculator. So given a velocity flow of 1 millimeters per second in the recirculator, we calculated the total flow rate through that, and then using that as the baseline, we calculated how much humic acid and how much coagulant we need to add into the recirculator to get a desired concentration, and then set the pump speed to get that concentration using the data from the Agro-Clara database.
And so Futurecast is pretty clear. We definitely need to test higher concentrations of humic acid and coagulant. Also, we need to take into account the time of experiments. We need to see, define exactly what the steady state means, and then stick to that, and then define how much time we're going to take for each experiment, and also stick to that, so we can have more standardized experiments. For any questions or recommendations, just email us, text us. Thank you.
Thank you.